72 million light-years away, a galaxy almost as wide as the Milky Way appears to have lost its invisible scaffold. NGC 1052 DF2 does not look like the galaxies that taught astronomers what a galaxy should be. In Hubble images it is a pale, almost transparent smear. Background galaxies shine through it. Its stars are spread so thinly that it has no obvious spiral arms, bright central bulge, or sharply defined disk. Yet the object is not tiny. Hubble measurements place it roughly 72 million light-years away and show a visible span of about 48,000 light-years, nearly half the diameter of the Milky Way. It contains only a small fraction of the Milky Way's stars. That makes DF2 an ultra-diffuse galaxy, broad in extent, faint in surface brightness, and difficult to weigh. Its ghostly appearance is striking. The deeper problem is dynamical. When astronomers tracked the motions of its compact star clusters, they inferred far less gravitating mass than ordinary galaxy formation models would lead them to expect. A system this large appeared to be held together mostly by the matter that could already be seen. Most galaxies are understood as luminous structures embedded in much larger dark matter halos. Dark matter does not shine, absorb light, or reflect it in a way telescopes can photograph directly. Its presence is inferred through gravity. Stars and spiral galaxies orbit too quickly to be restrained by visible matter alone. Galaxy clusters bend background light more strongly than their glowing gas and stars can explain. Across the universe, dark matter is thought to provide most of the matter and much of the gravitational framework from which galaxies grew. In that picture, the halo comes first. Ordinary gas falls into its potential well, cools, and forms stars. Remove too much of the halo and the usual assembly story becomes difficult. DF2 therefore matters for a reason larger than one faint object. If its measured motions genuinely indicate an extreme shortage of dark matter, then a galaxy can survive after losing most of the component usually treated as its scaffold. The object would not disprove dark matter. It would show that dark matter and ordinary matter can be separated on a galactic scale. A galaxy cannot be placed on a laboratory scale. Astronomers estimate its mass by watching how fast tracers move inside it. The stronger the gravity, the wider the spread of their velocities should be. DF2 is so faint that measuring the motion of individual stars is exceptionally difficult, so early studies used a small population of unusually bright globular clusters. Their reported velocity dispersion was low. That suggested little hidden mass beyond the stars themselves. But every part of that inference carries uncertainty. The sample of clusters is small. Membership matters, a foreground or background object can distort the result. The assumed distance changes the galaxy's physical size and luminous mass. The shape of the dark halo matters too. A compact halo and a very extended, diffuse halo can produce different signals in the limited region where tracers are measured. The clusters themselves are unusual, they are brighter than typical globular clusters, making them useful beacons but raising more questions about the system's origin. Researchers have also measured diffuse starlight and planetary nebulae to expand the dynamical picture. Each tracer samples a different radius and arrives with different uncertainties. When their velocities are compressed into one mass estimate, assumptions about equilibrium and orbital geometry become part of the answer. A galaxy recently disturbed by tides may not behave like an isolated, settled sphere. This is why the most accurate summary is not that DF2 has been proved empty of dark matter. Hubble's refined distance strengthened the case that it is unusually dark matter deficient, while later modeling showed that some diffuse halo configurations remain compatible with the available kinematic data. Soon after the first claim, critics focused on distance. If DF2 were much closer than reported, it would be smaller and less luminous, and its apparently low mass might look less extraordinary. Hubble observations addressed that by resolving thousands of aging red giant stars. The brightest red giants reach a recognizable luminosity, allowing astronomers to use the tip of the red giant branch as a distance indicator. The result placed DF2 near 72 million light-years away rather than at the much shorter distance proposed in some alternatives. NASA's Hubble summary says the revised measurements solidified the original team's claim and limited the galaxy to at most 1/400th of the dark matter expected under a standard scaling. That number belongs to a model-based comparison, not to a jar containing a measurable quantity of invisible particles. Still, it removed one of the simplest ways to make the anomaly disappear. DF2 remained large, faint, and dynamically strange. A related galaxy, DF4, appeared to share the same broad problem, suggesting that DF2 might be part of an unusual formation history rather than a single bad measurement. One proposed explanation begins with a violent encounter long ago. Dark matter and stars behave as collisionless components. Two streams can largely pass through each other, interacting mainly through gravity. Gas behaves differently. Gas clouds collide, shock, slow, and can be stripped into a compressed trail. In a high-speed encounter between gas-rich dwarf galaxies, the dark halos could continue onward while shocked gas remained behind. New stars could then form inside clumps of that separated gas, producing a chain of galaxies born with very little dark matter. Researchers have called this a bullet dwarf scenario, by analogy with the separation of hot gas and gravitating mass in colliding galaxy clusters. It is an active hypothesis, not a settled reconstruction. Other studies examine tidal stripping by the massive galaxy NGC 1052, unusual halo structures, or alternative interpretations of the sparse velocity data. The important point is that astronomers are not merely choosing between a normal galaxy and a magical exception. They are testing physical processes capable of sorting components that normally occupy the same cosmic structure. DF2 is unsettling because its evidence cuts in two directions. Dark matter was introduced to explain gravitational effects that visible matter could not supply. A galaxy with very little inferred dark matter might sound like an argument against it. In fact, separation can support the idea that dark matter is a distinct component rather than a bookkeeping error permanently tied to starlight. Yet the object also exposes how indirectly the invisible universe is measured. There is no photograph of DF2's missing halo. There are distances, stellar populations, cluster velocities, statistical models, and competing formation histories. Each new observation narrows the room for error without making the object simple. The observational challenge is severe because ultra-diffuse galaxies sit close to the brightness of the sky itself. Removing foreground stars, background galaxies, detector patterns, and scattered light can change which faint structures remain. A halo may be inferred from a handful of motions measured across years of telescope time. Recent work continues to model whether an extended halo could hide within present uncertainties, while other teams search for additional galaxies along the same apparent trail. The safest conclusion is precise: DF2 is an ultra-diffuse galaxy whose observed dynamics indicate an extreme dark matter deficiency under widely used models, but the amount and distribution of any remaining halo are still debated. If galaxies can be assembled after their invisible scaffolds and luminous matter part company, how many other ghosts are waiting below the brightness of our surveys?